Instituto de Física. El día de hoy tenemos el placer de presentar al profesor Marcos Pimenta. El profesor Marcos Pimenta obtuvo su diploma de graduado de licenciatura en Física y de maestría en Física de la Universidad Federal de Minas Gerais en Brasil. Posteriormente el diploma de doctorado en Ciencias por el Centro de Investigación de la Física de Altas Temperaturas del CNRS de Francia. Posteriormente hizo postdoctorado en el Massachusetts Institute of Technology en Estados Unidos y actualmente es profesor titular de la Universidad Federal de Minas Gerais, investigador 1A, que no sé qué significa, pero tiene el más alto, supongo, sí. Tiene experiencia en propiedades ópticas de materiales, principalmente, y ha trabajado en principalmente los siguientes temas: espectroscopía Raman, nanomateriales de carbono, sobre todo grafeno y nanotubos, cristales bidimensionales, perovskitas y transiciones de fase estructural. Es actualmente coordinador del Instituto Nacional de Ciencia y Tecnología de Nanomateriales de Carbono, del Centro de Tecnología en Nanomateriales de la Universidad Federal de Minas Gerais, y es miembro titular de la Academia Brasileña de Ciencias y de la Academia The World Academy of Sciences. Bueno, sin más preámbulo, les presento a Marcos Pimenta. Muchas gracias.
Buenos días. Es un placer muy grande para mí estar acá. Gracias a Andrés, a Laura. Me gustaría poder hablar la charla en español, pero me faltan palabras, entonces yo voy a cambiar a inglés. Si tienes preguntas, yo comprendo español, entonces puede hacer preguntas durante mi charla. Entonces yo voy a hablar principalmente... yo voy a cambiar para inglés. I will talk about resonant Raman spectroscopy. I will explain what's resonant Raman spectroscopy and with new types of 2D materials. And I will talk mostly about the works of my two PhD students, Bruno Carvalho and Eliel. And this is the group of my laboratory of Raman spectroscopy in Brazil. And we have collaborations with many different groups. And the group of Terones, Maurício Terones in Penn State, some groups in Brazil for doing theory, also groups in France where we are doing Raman spectroscopy, also in Brazil, this group, Graphene in São Paulo. And I will show, we have one or two papers with Andrés. I think that we have one paper together. I will talk about this paper, and hopefully we will have more papers in the future. And it was when André was in the group of Jean-Christophe Charlier. And also, we got some samples from China. Okay, then this is the outline of my talk. I will talk mostly about those three systems here. One is two layers of graphene that are twisted. This is a very hot and new topic because it was found recently that when you have a specific magic angle, there is superconductivity when you have only two layers of graphene that are twisted by 1 degree. Then I will talk about one paper that I will talk mostly about electron-phonon interactions in this talk, and I will show that in the case of twisted bilayer graphene, we can have intralayer and interlayer electron-phonon coupling. When one which connect electron-phonon in different layers and in the same layer. I will talk some works about those kinds of what we call transition metal dalcocogenide. This molybdenum disulfide, tungsten disulfide, and tungsten diselenide, studied by resonant Raman spectroscopy. I will also show some process in which we have what we call intervalley scattering of electrons, because in the case of those compounds, we have also one property of the electron, that's the valley in which the electron is localized. Then we will talk about intervalley scattering of electrons by acoustic phonons in monolayer and bulk MOST2. And finally, I will talk about the new type of 2D material that it's called black phosphorus or phosphorine. Then it's a structure where the atoms are phosphorus, And the difference between other 2D materials is that now we have a puckered structure and we have anisotropic properties in the case of black phosphorus. Okay, then you first talking about the Raman effect. The Raman effect was discovered in 1928 by this physicist from India, C.V. Raman. And the idea of Raman effect is the inelastic scattering of light. Then normally when we have a beam of light in a medium, most part of the light is scattered elastically. Then if I send, for example, a green laser, most part of the scattered light will be green. But a small fraction of the light is scattered with a different frequency or different energy. Then that's what we call inelastic light scattering. Then the point is that the frequency of the scattered light is different from the frequency of the incident light. And it was realized in 1928 by Raman that the difference in frequency between the incident and the scattered light was related to the frequency of some vibrations of the atoms. Then it was realized that in the case of the inelastic light scattering, the light is creating or destroying the quantum of vibration, of a vibration of molecules. In the case of crystals, then we can talk about vibration of the lattice, we can talk about phonons. Then the Raman effect, the most important Raman effect, is an effect in which we have the light that's creating or destructing phonons in the sample. And for example, this is if I send this scattered light in one spectrometer, then what you have, this is the spectrum where you have a very strong peak, is the elastic light scattering. But then C.V. Raman realized that there are some doublets here. There is one first doublet here, a second doublet here, a third doublet here. And each one of those peaks is associated to a normal mode, vibrational mode of the sample. And some peaks are below, have energy below the scattered light because the light, this corresponds to the creation of phonons. Then if there is creation of phonons, the scattered light has less energy than the incident light because part of the energy was used to create the phonons. But there is also one part here in which there is the annihilation of destruction of phonons. Then in this case, the energy of the scattered light is larger than the energy of the incident light because it also has the energy of the phonon that was destructed. But normally we work only in this part of the spectrum that we call the Stokes part that is related to the creation of phonons. Then I will show you many different spectra of Raman where I will show only this part. Then normally, Raman spectroscopy probes normally phonons or vibrations. Then it's somewhat related to infrared spectroscopy because infrared spectroscopy you are also studying vibrational levels or phonon levels. Then Raman and infrared, they are kind of complementary techniques to study the phonon spectrum of the vibrational spectrum in materials. Okay, now I will go a little bit deeper in the Raman scattering. In fact, Raman scattering is like that. It's a third order process because there are 3 steps. The first step is that there is one incident photon that interacts with with electrons and promote one electron from the valence band to the conduction band. Then the first step is what we call the creation of one electron hole pair. Then there is one creation of one electron hole pair. The incident photon is absorbed. There's the creation of one electron hole pair. This is the first part, the first step of the Raman scattering process. The second step is the interaction between electrons and phonons. There is interaction between electrons and phonons. And then, for example, the excited electron can interact with the lattice and create one phonon. Then there's the electron-phone interaction. And the third part is the recombination of the electron after creating a phonon, the recombination of one electron and one hole, and we have one scattered photon. Then this is the Raman scattering process from a more deep point of view. There are these 3 steps: creation of what electron hole pair, electron-phone interaction, and the combination of the electron hole giving rise to a scattered photon. Then this is the expression for the intensity of the Raman peaks. I don't want you to understand in details, but this is what we call the Fermi golden rule for a third order process. You know that the Fermi golden rule, when we have only two levels, the Fermi golden rule is the matrix elements of the perturbation between the initial and the final states. But then this is the third order process, and this is the Fermi golden rule. I would just want you to show that here in the numerator we have what we call the matrix elements of the electron photon, this process, the electron phonon, this process, and the recombination of the electron phonon. But then in the numerator we have the three steps. But then we have also two terms in the denominator that's given. EI is the energy of the laser, of the incident photon. EA and EB are the energy of the intermediate states A and B. Then one point is that every time the energy of the photon matches one electronic transition, when EI is equal to EA, then the denominator becomes small and the intensity becomes large. And when it can also occur with the intermediate state B, then I will show you that when we have the resonance is when EI is equal to EA, the denominator becomes small and the intensity becomes very large. Then that's what we call resonance Raman spectroscopy. Because normally Raman spectroscopy, Raman spectroscopy is used for many, many different purposes. But in most of the cases, we are dealing with what we call off-resonant Raman scattering. It means that the laser that I'm using is not in resonance with two electronic levels. This is the normal case of Raman scattering. But in the special case where there is a resonance, where the laser that I'm using is resonance with two electronic levels, then the denominator becomes small and the intensity becomes very large. Then what we have in my lab in Brazil, we have a Raman spectrometer in which we can change, we can tune the color of the incident laser. Then we have a set of different lasers, and some of them are continuous lasers, lasers that we can tune. Then what we do, as I will show, we can record the spectrum with many different laser lines. For example, this, we call this kind of what we call the resonant Raman Map. But then this is what, here in the horizontal scale is the Raman shift. And in the vertical scale is the energy of the photon. Then I'm using here, for example, this is red, this is a blue. Then I'm making many different spectrum from red, using the red to blue laser. And the color scale is the intensity of the peak. Then there is one peak here and another peak here. If I take only one energy, for example, the green laser, then I have the Raman spectrum. Here is I will show this the Raman spectrum of graphene. This is the G band, is here, and this the one band that we call T band. But if I fix the intensity of just one peak and follow how the intensity of the peak change when I change the laser energy, is something like that. Then in this case, what I'm writing here is the Raman excitation profile. Raman excitation profile is the intensity of this band here, the G band, when I change the laser energy. Then you can see the band becomes very intense, and after that becomes slow. Then the point is that when we do Raman spectroscopy with just one laser line, we have the Raman spectrum, and we can get information about phonons. But now, when I study the Raman excitation profile, I can study the properties of the interaction of phonons and electrons. Okay, then I can have also information about electrons when I do resonant Raman spectroscopy. Then that's when Raman spectroscopy with just one laser line is very useful to study all kinds of materials, but in special graphene and 2D materials, because we can get many important information like about disorder, defects, presence of doping, charge, strain, the structure of the edge, number of layers. It's very useful to get all those properties. But when we are able to have many different laser lines and to tune the laser line and to follow the intensity of the peak when we tune the laser line, is what we call resonant Raman spectroscopy. Then we can also probe the electronic structure. We can also probe the phonodispersion, excitons, and mostly what we call the electron-phono interaction. Okay, then I will start about graphene. And this is the structure of one layer of graphene. This is the direct lattice, the real space. When we go to the reciprocal space, this is the reciprocal space of graphene. And here in blue, we have the first brilliant zone of graphene. The center of the brilliant zone is what we call the K point, the gamma point. And we have also the corners of the hexagon that are the K points. And in the case of graphene and also many other 2D compounds, the properties of the electrons near the K point are very important because they are related to the optical transitions. Okay, then that's what I'm going to show now is the band structure, the electronic band structure of graphene. This is then the first brilliant zone, and I'm representing the electronic dispersion, the first brilliant zone. It's like that. This is the first brilliant zone. Here is what we call the Fermi level. Below the Fermi level, the electronic states that are occupied, and above the Fermi level, the electronic states are not occupied. Then below the Fermi level, here we call the valence band, and here we call the conduction band. And one very special property of graphene is that the electronic structure near those corners of the brilliant zone have a linear dispersion, like those conical those cones. Then we have one cone here near the K point, another cone here, what we call the K prime, because it's a different K point. Then this kind of linear dispersion is probably one of the most important, most interesting properties of graphene, and gives rise to a very interesting physics. And in special, we can map the electronic structure of monolayer graphene with the so-called the Direct equation. The Direct equation, remember that the Direct equation is the equation that's at the same time relativistic and quantum relativistic equation for describing electrons. And in this case, this is what we call the one Direct fermion without mass, because when we have this kind of dispersion, it means that there is no mass. It's a Direct with no mass, since we have those cones, they touch each other at the Direct cone. Okay, now I will talk about Raman scattering in graphene. Raman spectrum in graphene, there are two this is a sample, a good qualitative sample of graphene. We have two peaks. This we call the G peak, and this we call the 2D peak. The G peak is very easy to understand from this view graph here, because in the case of graphene, in fact, we can understand this honeycomb structure as two lattices, one formed by the red atoms and the other one by the green atoms. They are not equivalent because there is no translational symmetry that brings one in another. But then we can see that in fact graphene, we can consider that we have two sublattices. One formed by the red atoms and the other formed by the green atoms. And one sublattice is vibrating against the other one. It's vibrating like that. And this vibration has a given frequency. And this vibration is the vibration that gives rise to the G band. Then the G band is the stretching mode of the carbon-carbon atom vibration. But we have also a very interesting process, a very interesting band in graphene that we call the 2D band. And the 2D band is it's a higher order process because it involves electrons in different cones of the brilliant zone at the K and the K prime. And I don't have time to explain in details, but this band is like that. One incident photon is absorbed by creating one electron hole pair. The electron is promoted from the valence band to the conduction band. But then there is one strong electron-phono interaction. The electron is scattered from this point to another point by emitting a phonon with a large wave vector, that is one electron scattered from here to there. The whole is scattered from this point to that point, and here there is the electron phonon recombination. You see that this is a fourth order process because I have 4 arrows here. It's a higher order process, but it was realized that then this is a higher order process that we can have in the denominator now 3 terms, and those 3 terms, they can be resonant simultaneously. Then that's why we get a very strong peak. And this is the signature of single-layer graphene, is the fact that the 2D peak is stronger than the G peak, even though this is a normal, normal process, and this is a higher order process. And this peak is very useful to get information about graphene and other 2D materials. And for example, what happens if I change the color of the laser? This is the one monolayer graphene where I'm changing the color of the laser. This is the red laser, yellow, green, blue. And you can see that now the position of the peak change when I change the laser. But one thing that I would like to say is that the Raman spectrum, the Raman shift, this difference between the Raman peak and the peak of the laser. Then, since it is a shift, normally the peak, the position of the peak in the Raman spectrum does not change when I change the laser because it's only a shift, only a difference. But in this case, we have the dispersion of the peak. This is a very unique and interesting phenomenon. And the explanation is like that. If I'm using a red photon, then the electron hole pair is created in this point. And the phonon that brings the electron from this point to that point is the size of the red arrow. If I had the green photon, then the phonon has a larger wave vector, is the green arrow. If I have a blue photon, the resonance occurs in that point, then the phonon has a still larger wave vector. And okay, this is what we call the phonon dispersion of graphene. Then in the case of graphene, we have 2 atoms per unit cell. Then we have 6 phonon branches. 3 of them are the acoustic phonons, acoustic branches, and 3 are the optic branches. Then this is just to show that if I put those arrows here in the phonon dispersion, what I'm probing points, I'm probing the phonon dispersion of this, what we call the transverse optic phonon. And that's why I see this kind of dispersion. Then the idea is that we can, using this 2D band, we can probe phonons in the interior of the brilliant zone of graphene. Okay, but now what happens if we have 2 layers of graphene? Then the properties are completely different. For example, here I have bilayer graphene, but in a very precise stacking way, what we call the AB stacking or Burnout stacking, in which one atom of the top layer is on the top of the atom of the bottom layer, but the other one is not. For example, the blue atom is not on the top of the red atom. This is what we call Burnout stacking, and this is the stacking of graphite. Graphite would be AB, AB, AB is a crystalline graphite. And you see that now the electronic dispersion is no more linear, as in the case of one layer, has those parabolic shape. Since we have two layers, then we have two bands, 2 valence bands and 2 electronic bands. And this is manifest in the shape of this 2D band. You see, I showed you that the 2D band in one layer graphene is a very strong peak, but when I have bilayer, you can see that the band is composed by different processes, like I showed you. You showed me one band similar to this one, is not symmetric and composed by peaks, is because in the case of bilayer graphene, since we have two valence bands and 2 electronic bands, we have 4 different possibilities of this of the process that I showed you. Then I showed that the shape of the band is very useful to distinguish the number of layers. If I have 1 layer, 2 layers, 3 layers, by the shape of this band, we can get information about number of layers. Okay, another important thing in graphene, what we call the disorder-induced band. For example, here, when I have the spectrum of many different samples of graphene with different size, When I have a very big sample of graphene, I only have the G band. But when I have a very small sample of graphene, like this one is 20 nanometers, it appears two new peaks, one here that we call D, and another here that we call D prime. And those bands appears only when we have defects. For example, this is the Raman image of the G band. Raman image, it means that this is a piece of graphite, okay? Then I'm collecting only the light that comes from this peak. I put one filter and I collect only the light that comes from the G peak. Then I have the G band image, is the image of the G band. But I can also probe only the light that comes from this part here, is the image of the D band. And you can see that in the center of the sample, since there's no defects or no disorder, I don't see the signal of the D band, but near the borders or when we have defects, the D band appears. Then the D band, we need to have defects to see the D band. And why it occurs? For example, now I'm showing the Raman spectrum of a bad sample of graphene, disordered graphene with defects. Then we have more than the G and the 2D bands, we have the D and the D prime band that are bands that appear only when I have defect. And the process for the D and the D prime are very similar to the case of the 2D, but now, in the case of the 2D, you remember that I have two phonons, but now I have one phonon. Then the electron first is, we have a creation of one electron hole pair. The electron is scattered from this point to that point, to the K prime, but then the defect is allowed to scatter back the electron from the K prime to the K. And this kind of thing is elastic scattering. It's like if I send a ball in the ball will come back, is one elastic process. Then when we have defect to scatter back the electron from this point to that point, then I have the D band. But then you see that in this case, the D band involves the direct cone K in the direct cone K prime. That's we call the inter-valley scattering, because the electron is scattering from one valley. I say that when the electrons are in those cones, they are in a valley K. They're scattering from one valley to the other valley here. But we can also have what we call the intra-valley scattering. Then the electron is scattering from one point in the valley, in the K valley, to another point in the same valley. And I can...
It has to be a special kind of defect for that thing to happen, or any defect can do that?
In principle, any defect can do that. But we can, there are some, for example, from the ratio between the intensity of this and that one, we can distinguish different kind of defects. But can be punctual defects, can be edges, can be any kind of defect gives rise to those peaks. But
cross-sections, they have different cross-sections.
They have different cross-sections. Then the idea is exactly that. They have different cross-sections, but then all defects. But then you can see that this, what we call the inter-valley scattering are phonons that are close to this is the phonon dispersion, close to the K point. Then that's why the frequency are here at 1350 wave numbers. And the D prime is the band that comes from this branch here. That's why it's a little bit, the position is a little bit above the G band. Okay, now I will talk about what happens in the case of twisted bilayer graphene. Twisted bilayer graphene, then, as I told you, is different from Burnout stacking, because the Burnout stacking, they are in a very precise way to be stacked. But here is just two layers of graphene that are rotated, one with respect to the other one. This is then one layer is by those gray balls, the other one the blue balls. And you can see that when we have two twisted bilayer, it appears one kind of superstructure. This is like an interference. It's called Moiré pattern. The Moiré pattern, every time you have two periodic things, when you superpose, you can see some beatings, like the beating of the sound. But in the case of the Moiré pattern, you see that there are those kind of hexagons here, this kind of structure. Then what we have here a superlattice, a superstructure, okay? Now, let's go to the reciprocal space. Every time we have something that is a superlat, is the real space. In the reciprocal space, we have a small thing. For example, here, I'm putting here in gray is the brilliant zone of one layer, and black, the brilliant zone of the other layer, okay? And you can see that the Q1, Q2, and Q3 are the vectors that connect the reciprocal lattice of one layer. The reciprocal vectors of one layer is the gray layer, the reciprocal vector of the black layer, and this Q1 is the vector that connects those 2 points. And I can show that in the case of this superstructure, we have also what we call the reduced brilliant zone. This is the red one, is the brilliant zone of this superstructure, is the red one. And we have those Q1, Q2, and Q3 that are the wave vectors of the moire pattern. Then we have the moire pattern here, and we have then the wave vectors of the moire pattern are those red vectors. Okay, but there is a very interesting thing that was found some years ago, is that when you have, then we have here the black one, 2 layers, the black one and the red one. Then I have the direct cones of one layer and the direct cone of the other layer. For example, here I'm seeing from the top the direct cone of the 2 layers, here from a lateral view. But then what was first predicted theoretically and after that observed that there is an interaction between those 2 cones of the 2 layers. And the interaction gives rise to these flat bands. Then when is the crossing of the two cones, they interact, then they have those subbands. And they give rise to some new kind of optical transitions. Why? For example, here I'm showing this figure, what we call the density of electronic states. First, the blue one is graphene. Graphene is the blue, is related to the fact that we have this kind of conical dispersion. The blue is graphene. But when I have 2 layers of graphene twisted by layer graphene, like this one, it appears this kind of, when I have flat bands, what we call Van Hove singularities. We have those kind of Van Hove singularities. And you can see that the distance between those Van Hove singularities is proportional to the twisting angle. Then I can tune the position of those peaks by just changing the angle between those 2 layers. And it was realized in this paper in 2014 that we can have optical transition between those peaks. And for example, the figure is not so good, but there's the energy of this is a experimental observation of the optical absorption in this twisted by layer graphene. This is the angle. Here is 10, here is 30. And this is the energy. For example, 2 electron volts is red, 3 is blue, and here is infrared, UV. Then we can see that we have one optical transition that we can tune simply by if I have sample with different angles. Then one thing that was realized in those 3 papers is that if I'm lucky to have one laser that is in resonance with those singularities, then we have the resonant Raman condition. Then the intensity of the peaks become very, very intense. For example, those 3 experiments are about the same, but you can see here, for example, in here in this case, the intensity of 2 layers divided by the intensity of 1 layer. Normally, we would expect that there would be about 2 times, because I have 2 layers, 1 layer, the signal would be only 2 times stronger. But in the case, you can see that the signal, it can be 90 times stronger. That's why, in this case, I was lucky. This is the red laser, this sample at 10 degrees. I could see that when the laser is in resonance with those singularities, I have a very strong, I have a resonance effect, and the peak becomes very strong. And another important work that was done, and here we have also there is a Jessica Campos that worked in this problem. It was new peaks that appear in the Raman spectrum of twisted bilayer graphene. The point is that since the Raman when I have the separate structure, then the reduced brilliant zone is small. Then I have new peaks that appear because the peaks that were in the interior of the brilliant zone that are folded to the center of the brilliant zone when I have the separate structure. And those peaks, they are related to the fact that we have this moire pattern. Okay, then it was in this paper in 2011 from our group, we proposed that this process was similar to the process of the 2D and the D band, but instead of having defect or a second phonon to scatter back the electron from this point to that point, the electron was scattered elastically by the moire pattern. Then the moire pattern was provided elastic scattering to bring back the electron from one cone to the other cone. Okay, now I will show some results in samples of twisted bilayer graphene. Then there's something that Laura she's doing samples of graphene, very nice samples of graphene here. And by changing the parameters of the system, if you can also synthesize this kind of sample. This was done in China. But you can see many hexagons, and the light part is one layer, and in the center we have a second layer. Then we have twisted bilayer graphene. For example, this is the best to see. Here is one layer. In the center we have a second layer. And since the shape of the samples, they are hexagonal, we can estimate the twisting angle. And after that, do Raman spectroscopy. Okay, then what I'm going to show here is one sample of 6 degrees, another sample of 13 degrees. In this case, we could see the G band and a new peak that we call the LA band. And you see the G band here is 2 times of twisted bilayer graphene. The intensity of the G band of twisted bilayer graphene is 2 times the intensity of single layer. That's a normal and non-resonant process. But if I have the 13 degrees laser sample, if I change the laser and I see the Raman spectra, I can see this huge enhancement of the G band and also the appearance of this TE peak. Okay, then I don't have time to go into details, but what we could see, that are 2 different kinds of peaks that appear. One that appear when the G band is not in resonance, and the second one that appears when the G band is in resonance. Then what we showed in this work, that in fact we can have this double resonance process, as I showed you, this kind of process. But in one case, the electron is scattered from one point in the Dirac cone to the other point, the Dirac cone of the same layer. You see here the same cone from black to black. Then that's called the intra-layer process. But we could also see that we can have a process that connects the electron from one layer, from the Dirac cone, from the one layer to the Dirac cone of the other layer. Then this was the interlayer process. Okay, then this was the calculation of the energies for the intralayer in the interlayer process. This I can explain details after that. We have here the transitions of the interlayer and the intralayer process. In fact, we have 2 for each case. And here is the energy of the interlayer process as a function of the angle from 0 to 30 degrees. And here is the phono dispersion of the LO and the TO band. Then what we could show in this paper is that we could see, for example, here, using visible laser, that the peaks that are below the G band, those peaks, they are enhanced by the interlayer process, and the peaks that are above, they are activated by the intralayer process. Okay, then we did some measurements using also infrared laser, because if you need to study low angles, you need to use infrared lasers, and we could put some points here showing that we can have both processes. And for a higher angle, then we need to use UV Raman, because then UV Raman you can see angles close to more than 20 degrees. Okay, but then in this case, and after that, what we did, we put graphene on the top of HBN. HBN is the hexagonal boron nitride. Then we can put graphene, and we can also study the angle between graphene and HBN. And we could show that even in the case of graphene on the top of HBN, we can see the appearance of those side bands. And those side bands, they are signature of the intra-layer process. Then in this case, we could show that when we put graphene on the top of HBN, there is also this moire pattern. And the moire pattern impose one potential to graphene, and this kind of potential can activate new peaks. Then in this case, what we call that we see the intralayer process observed in graphene on the top of HBN, and there's a signature of the interaction of those two layers. Okay, now I will explain transition method alkyl-coordinates, and probably if you have this machine shop here, probably you see that they have this kind of lubricant. It's a solid lubricant that's molybdisulfide. It's known for many, many years. That's a mineral. It's called molybdenite. But it was only a few years ago, probably 10 years ago, that people decided to exfoliate molybdisulfide. And this is the structure of molybdisulfide. Those are layers. Each layer here is, the molybdenum is the black ball, and the yellow ball the sulfur. It's called transition method alkyl-coordinates because we have a chalcogen. It can be sulfur, selenium, tellurium, and we have transition metals, and those are probably the first that we studied: molybdenum, tungsten. And the different point of these compounds that they are semiconductors, because graphene is very nice for many things, but for digital electronics is not useful because you don't have a gap. Then you cannot do the transistor, FET transistor 0101. But those compounds, they are semiconductors. Then they are very useful because you can do study 2D materials, but some of them are semiconductors. Okay, just to show from the Raman point of view, now we have two different peaks. One is the vibration of the sulfur against the metals. Then it's what we call in-plane mode. It's the E mode, that's the in-plane mode. And we have also the A mode, that's out-of-plane mode. Then in one case, the atoms are vibrating in the plane. In the other case, the atoms are vibrating out of plane. Just for comparison, this I'm comparing here graphene MOS2. This is the formal dispersion of graphene. Then you can see that we have those 6 branches. In the case of MOS2, we have 3 atoms per unit cell. Then we have 6 phonon branches and 3 acoustic branches. This is the formal dispersion of MOS2. In the case of graphene, as I showed you, we don't have gap. But in the case of MOS2, we have one gap here. But probably the most interesting thing in MOS2 and also in those compounds is that the gap, the electronic structure changes when you change the number of layers. For example, when you have bulk MOS2, that is a very studied bulk MOS2, you see that the top of the valence band does not coincide to the bottom of the conduction band. Then we have here what we call the indirect semiconductor, like silicon. Silicon is indirect semiconductor, and silicon is very good for doing devices, but it's not good for doing optics, because we don't have the silicon is not good for doing lasers or things like that. But in the case of molybdisulfide, there is what happens that now the top of the valence band coincides with the bottom of the conduction band. Then we have what we call the direct gap semiconductor. Then this is important. When I have the direct gap, can have emission of light. This is like the case of those 3,5 compounds, that this laser is made by those 3,5 compounds. Then when you have direct gap, you can also use for doing optics, for doing light emission. But the MOS2, there are many different interesting things. One is there is a very strong spin-orbit coupling. Then the spin-orbit coupling splits, for example, the top of the valence band. Then we have here, due to the spin-orbit coupling, you have the splitting of this band here, near the K point. And another important thing is that now, in the case of 2D materials, since the electron, when I have one excited electron, and live in one hole, the electron and the hole, they are in the same layer. There is a very strong Coulombic interaction between the electron and the hole. Then when we have this bonded electron-hole pair, because they are interacting, we have what we call exciton. Exciton is one bonded pair of electron-hole pair. We can think about like the hydrogen atom. The hydrogen atom, we have one electron and one proton. They are separated. By the electron and the proton, they attract each other, forming the hydrogen atom. And then you have the electronic levels of the hydrogen atom, 1s, 2s, 2p. And in a similar way, we can consider that now in the case we have excitons, and we have those fundamental and excited states of the exciton due to the fact the electron and the hole, they are strongly bonded because they are in the same layer. Okay, now this is the resonant Raman spectra of MOS2. Then we did that. This was the paper of Bruno Carvalho. Then we have 1 layer, 2 layers, 3 layers, and 4 layers. Then, as I showed you, using many different laser lines that are the color of the spectra are about the color of the laser. And then here it's what I call the resonant Raman excitation profile. For example, here I have this A mode is the so-called out-of-plane mode. The A mode, and the E mode is the in-plane mode. Then what I'm plotting here, for example, is the intensity of the E mode and the A mode when I change the laser energy. For example, let us see in this case, I will show that, I think that then the white dots are the E modes and the black triangles are the A modes. Then I will show that this figure in details. Then what we could see is that but one thing that let me go back. I forgot to say one thing. In the case of those compounds, we have 2 excitons that we call the A exciton and the B exciton, because the A exciton would involve transition from this point to that point, and the B exciton from this point to that point. Then when you see the optical absorption spectrum of moly disulfide, we can see this B exciton, and here is the A exciton. Okay, then those are the most important features. And Laura, she could measure. It was in this compound. You could see probably one of those, probably the A exciton in your measurement. The A. Okay, then this is now the Raman excitation profile. Then this is the A exciton, B exciton. There is also a third exciton that we call the C exciton here. Then what we could see is that for the in-plane, the out-of-plane, that the out-of-plane mode was interacting with the A exciton. We can see that when you have resonance with the A exciton, the B exciton, then we have the enhancement of the out-of-plane mode. But the in-plane mode was not enhanced by the A and the B exciton, but both of them were enhanced by the C exciton. Then what we realized here is that why only the out-of-plane mode is enhanced by the A and B exciton is because we have some the electron phonon coupling is symmetry dependent. Not all phonons couple with all excitons or all electrons. It depends if the matrix element of the electron phonon interactions is strong, and if the matrix element is strong, then we have the enhancement, or in other case, we don't have the enhancement. Okay, then this is
the lifetime of the excitons depends on what?
The lifetime of the exciton. I think that mostly probably relate to the presence of defects or the environment, because the exciton, they're very strong influenced by the environment. The substrate, depends if the sample is suspended or on the top of different kind of substrate, because the fields of the electric field, they go to the substrate.
The widths are very much dependent on it.
The widths are very much dependent on that, that's right. And that's one question that Laura was asking me, because then how can we get information about the width? But then it depends a lot on not only the width, but even the position depends on the environment. Okay, then the conclusion is that we could observe that some phonons couple with excitons and another one does not couple. Then that's what we call the symmetry-dependent electron-phonon coupling. And we did similar experiment now with tungsten disulfide and tungsten diselenite. They're very similar compounds. And this is the Raman spectrum of tungsten disulfide and tungsten diselenite. And what we realized here is that, for example, in the case of tungsten disulfide, we have the enhancement. This is a totally symmetric mode with the A and B exton, and it was a very normal behavior. But we realized that in the case of tungsten diselenide, we could not see the enhancement with the B exton. And that's where Andres worked with us. It was a calculation that was done. Basically, the idea is that in the case, despite the fact that the only change from sulfur to selenium, the electron-phone interaction changed a lot. And then it was shown by the calculations of Andres that, for example, in the case of tungsten disulfide, we could see the enhancement of the peak by the A exton, but in the case of the tungsten diselenide, due to the fact that the electron-phone coupling is not so strong, we could not see the enhancement. Then the theory explained our experimental results. How? I think that 5 minutes. Okay. Then probably I will not talk about black phosphorus, but then I will talk more sophisticated behavior of MOS2. Then this is the same sample of one layer of molybdisulfide excited with the green laser. That I think that the green laser that you have here. Then you can see those two peaks. There's a normal Raman spec. The E peak is the in plane, the vibration of the atoms in the plane, and the A peak are the vibration of the atoms out of plane. These are not at the resonance with the exton. But now, the same sample, I'm just changing the color of the laser. I'm using a red laser, and you can see that now the spectra is completely different, because now, in this case, we are near the red laser is in resonance with the excitons. Then we have a completely different spectra, and this band, it becomes very strong. And you can see that this band here, the energy is 460 wave numbers. And when you see the Fonneau dispersion of, this is the Fonneau dispersion of molybdisulfide. Okay, then the A and E modes are here at the center of the Brownian zone. Those are those peaks here. But this 2LA band comes from phonons of the longitudinal acoustic branch near the M and the K point. Okay, and here is 230, but when you have two phonons, we have a higher order process. Then we have two phonons of the 230, then we have 460, and then this band is known for many years. That was related to 2 times the longitudinal acoustic phonons near the M and the K point. But what we did, that's the paper of Bruno, that we did, this is now the same kind of the Raman spectrum in that region. Here's the Raman shift. Here is the color of the laser. Now we are using a tunable laser. Then we can, this is from red to yellow, but then we can see here the enhancement by the A exon and the B exon. But then the most important thing that we could show here is that there is also this kind of dispersive behavior. For example, when you have the normal modes like this, the A and the in plane out of plane, the position does not depend of the laser, but there are some peaks that depend on the position of the laser, and this is a signature of the process, the intervalley process that I showed you. Okay, then we can see that in fact this 2LA band, it's composed by different contributions, and we could fit the data with different contributions. And in this graph here, we have the frequency of the peaks as a function of the laser energy, and you can see that we have this kind of dispersive peaks. Then it's a new kind of phenomenon. Then that was explained as in the case of Rapine by this kind of process, this intervalley process. For example, in the case of one layer of molybdisulfide, we have one valley near the K point, another valley near the K prime point. The dispersion is different from graphene, that's linear. In this case, we have a gap, a semiconductor, but we also have the process, the same kind of process that appears when we are real resonance, that showing that we have also peaks that come from the transition of one valley to the other valley. And this was a theory that was done by the group of Vincent Crespi in Penn State and Yuan-Shi Wang. They calculated this so-called this intervalley process, and they could show the calculation. They could show that some peaks, they are dispersive, explaining our results. And finally, the last thing that I will show you is that here is the Raman spectrum of 1 layer, 2 layers, 3 layers, and 4 layers. And you can see that the shape of this 2LA band, in the case of 1 layer, is completely different from 2 layers, 3 layers, and bulk. And you know that from the electronic point of view, the difference between 1 layer and 2 and more is the fact that in one case we have the direct gap, and the other one we have the indirect gap. For example, here is the case of the direct gap here. The minimum of the minimum of the conduction band when you have 1 layer are at the K and the K prime points. But in the case of bulk, we also have one valley in this point that we call the Q point. Then now, in the case of bulk, 2 layers and 3 layers, we have 2 different kinds of valleys. Not only valleys at the K point, but we have valleys at those points, Q points that are between K and gamma. And what we could see is that in the case of scattering from K to Q, for bulk, it's possible because we have here the minimum of the K band. Then we have this process from K to Q. That's possible in bulk and 2 layers and 1 layer. But in the case of 1 layer, we cannot have the scattering from K to Q because the valley here is not deep enough. Then what we could show is that in the case of 1 layer, we can only see the scattering from K to K prime, is this one, K to K prime. And you see the phonon that brings the electron from K to K prime. The vector of the phonon is near the K point. But in the case of bulk, we can have the scattering from K to Q. And if I bring the phonon from K to Q, is the phonon that are close to the M point. Then in the case of, differently from the case of graphene, which we only have the scattering from K to K prime, in the case of moly disulfide, 2 layers, 3 layers and more, we have also the scattering from K to Q that are related to the phonons near to the M point. Okay, this part I will skip, but then the next time you invite me, I will talk about black phosphorus, okay? The only point of black phosphorus that probably it's interesting to show that because since the structure is not symmetric, we need to do polarized Raman. Because normally I didn't talk about polarization of Raman, but when you have an isotropic, then we need to play with the polarization of the incident light and the scattered light, and we have this kind of plots. Now here is the angle, okay? I'm just rotating the sample, and the intensity of the peaks when I'm changing the angle. Okay, but then this part I will skip. Then I came to my conclusions. Then probably the idea is that Raman spectroscopy is a very useful tool to study materials, 2D materials. But if I'm able to change the color of the laser, I'm doing resonant Raman spectroscopy, then I can get more information, mostly about electrons, excitons, and the interaction between electrons and phonons. Then the specific conclusions that the new peaks that appear in the spectra of twisted bilayer graphene are enhanced by 2 different mechanisms. The intralayer and the interlayer electron phonon process, where in one case where everything is occurring in 1 layer, the other case there is electrons from different layers. The interlayer process is observed also when I have graphene at the top of HBN, and might occur whenever graphene is in contact with a crystalline surface. In the case of moly disulfide, we could also observe this intervalley process that we call double resonant process. The intervalley process from K to K prime involve acoustic phonons near the K point, but in the case of bulk, we can also have the process from K to Q involving phonons near the M point. And this is a consequence of the the direct to the indirect band gap transition, we can get this information from the analysis of the 2LA band. Okay, thank you very much for your time.
Thank you, Marcos. Do we have any questions from the audience?
Yes, yeah, I was actually very interested in hearing you talking about. Okay. I was actually very interested in hearing you talking about the black phosphorus, since my partner here and I were discussing an article about another compound, which is in Spanish sulfato de estaño, which in the article they are discussing the polar sulfato de estaño, tin sulfide, tin sulfide, in which they make a polarization result Raman spectroscopy, and it all comes down to the fact that the anisotropy of the compound is pretty much the same as black phosphorus, but that is as far as they go. They do not make any sort of a discussion about why the particular geometry of black phosphorus leads to these anisotropy properties, and how with polarization result Raman spectroscopy one can find these really important properties. So I was actually hoping for you to talk about.
Sorry, okay, then
it would be really, really interesting.
Yeah. Yes, the point is that for example, in the case of black phosphorus, now we have for 6 Raman active modes, those 6 Raman active modes. But when you send the light perpendicular to the layer, we have only 3 modes. Those 3 modes that we call AG1, AG2, and B2G. And those are this AG1, B2G, and AG1, B2G, and AG2, those 3 peaks. Then, the point is that when you have an isotope, you need to use polarization of light. And the polarization of light is given by that what we call the Raman tensor. Yes. Okay, the Raman tensor. Then we need to consider Raman tensor. For example, it comes from group theory. For example, in the case of the AG mode, the Raman tensor is this diagonal tensor. For the B2G, the Raman tensor is this of energies. Then, normally, what we have, for the angular dependence, we need to consider the polarization of the incident light and the polarization of the scattered light, okay? And the intensity is given by this expression here. Here is the product of the polarization of the incident light, the scattered light, and the Raman tensor. And the Raman tensor is a derivative of the dielectric constant with respect to the normal coordinate, okay? Then, you have like something like that. Then, okay, now in fact, what we realize in this work is that if you consider Raman tensor elements only with real components, you cannot fit the data. But in this case, we realize that the Raman tensor is a complex number with one real and imaginary part, was one amplitude and phase. Then, if we put those Raman tensors for the AG mode and B2G mode in this expression, then normally we consider two configurations to explain. One of them is where the incident light and the scattered light are in the same direction. That's the parallel configuration. In the other situation, we cross the polarization of the light, okay? Then, in this case, we can have, for example, for the AG mode, the intensity of the parallel and the scattering for the AG, and the same thing for the other one, for the B2G. Then we have this kind of, this is the expression. Then we need to fit the data. Then, for example, we could fit the data for the black phosphorus in it, and from the fitting we get the value of the Raman tensor elements. Then the Raman tensor depends on the symmetry. Each symmetry there is a Raman tensor. The group of black phosphorus is the orthorhombic group. Then I think that, I'm not sure about this tin sulfide, but I know that germanium selenide, germanium sulfide, they have this orthorhombic structure. Okay? Then they have the same kind of behavior. But then in order to, when you have an isotropic crystal, you need to do polarized Raman. If you do Raman without taking care of the polarization of the scattered light and the incident light, we can get some result. And that's what we get normally is what is that. This is, for example, this is the, for the parallel configuration, and this is the crossed configuration, and I'm rotating the sample from 0 to 330, then you see that the intensity of the peaks appear, becomes strong and weak, okay? And this is the parallel and the crossed. Then, in order to get the Raman tensor, you need to do those two experiments. You need to feed the data, then you get the Raman tensor. And also we have a new paper that just appeared in PRB, practically but with germanium selenide. And now I have one student that's studying the more complicated system, that's rhenium disulfide, because rhenium is triclinic. Then it's another symmetry, then it's...
So you...
Maybe continue the discussion.
We can.
Just to give chance for others.
At the beginning, you just said that this Raman technique was sort of complementary to the infrared absorption. So my question is, if the infrared absorption gives you some information about this type of behavior of the electrons, the excitons, or not at all?
No, because the point is that
Not possible.
the point is that in the case of infrared, you don't have the electron-phone interaction. You have because probably I don't have.
Yeah.
I think that I have one view graph here that will explain this very easily. I will probably it's.
So this is only unique. That's what I'm trying to say of the resonance Raman scattering.
Yes, this is
Okay. No, that's
probably this. I can show you, for example, this view graph here. It's good for explaining.
And the other question was, how do you, I mean, if you need a specific model to take into account the electron-phone interaction between the two layers. You have this electron-phone interaction between the electrons in one layer and the other layer, but the interlayer.
The interlayer, yes.
How do you model this for the electron-phone interaction?
Okay, let me first go to your first question. Okay, then, for example, this is just a very simple example of a harmonic oscillator. Then you have vibrational levels. Infrared spectroscopy is a transition from one vibrational level to the other vibrational level. Then I have just one transition from here to there. In the case of Raman spectroscopy, then I just send the electron from one point to the point to an excited state, and it brings back the electron here. The final process is the same, okay? Then it's from here to there. But the selection rules are different. The selection rules are different because in this case we have one only transition. In the case we have, in fact, three from here to there, and the creation of one quantum. Then in some situation, there is one thing that we call the exclusion principle. If the system has inversion symmetry, infrared is one odd process, and Raman is even process. They cannot coexist. Then peaks that appear in infrared, they do not appear in Raman. But if you don't have inversion symmetry, it can happen that one peak can appear in both infrared and Raman. Then by comparing Raman and infrared, we can get information about symmetry. But the difference, because the selection rules are different. Then different phonons are involved in infrared and Raman spectroscopy. And your
I think we have to stop because we have run out of time.
Okay, sorry.
And a lot of people need to leave.
Okay.
Things.
Okay.
Thank
you very much.
Thank you, Marcos. Anyway, Marcos will be around for the rest of the afternoon, so you can approach.
Very nice talk.
Okay.
Hi.
Thank you very much.
Very nice talk.
Thank you very much.
presentation.
Thank you very much.